review in chapter 3 we were talking about axial forces, right? So we had a member and we had a force which was an axial force. So when you have an axial force, you're gonna have a deformation, right? This deformation was called elongation. In chapter 4 we had torsion. So because of the torsion, you were observing a, a twisting, right? So you were calculating angle of twist. And in chapter 7, you will have shear forces and bending moments. Because of which you will have displacements and bending angle. So depending upon the loading condition, you have a different kind of deformations. In chapter 3, you had axial loads, and you saw what axial loads did to the member. It basically elongates. You had seen elongations. When you had torsion, you saw twisting, and we calculated angle of twist. In chapter 6, we calculated shear stresses because of the shear force and bending stresses because of the bending moment. In chapter 7, we're going to see how these shear forces and bending moments cause deformations. And basically, they cause two types of deformations. One is called displacement and one is called bending angle. So this displacement is referred by this symbol and the bending angle is referred by this symbol. So to explain further, I'm gonna just draw two simple cases where you have shear forces and bending moments, and we'll see how it affects the deformation of the member. So I'm gonna draw a cantilever beam, and you have a load P. So you can try to imagine how the deformations would look like because of the load. So I'm going to draw a deformation curve. We also call this elastic curve. So if you try to draw or if you try to imagine how this beam will bend, so this is how it will bend. So, so originally the cantilever beam was straight. You applied a load and then it just kind of had this curve shape. So this shape is called elastic curve. And this distance is called displacement. And you also have, if you try to take a slope at any point, so for example, if I want to take a slope at this point, so how you calculate slope is you take a straight line and you make a tangent, and this is called theta. So this is theta, which is bending angle. So because of the shear forces and bending moments, you're gonna get something we call elastic curve. So when you have this elastic curve, you're gonna see displacements, and you also are gonna see bending angle. So the displacement is basically the vertical uh, movement because of the load, and the slope of this displacement is called bending angle. And you have an equation for these displacements and the bending angle. So I'm going to write the equations, and these equations you will need to solve for this bending angle and the displacement. So the bending angle you can calculate using this formula, 1 over EI and integration of moment dx. So you can calculate bending angle at any point using this equation. And you can also calculate displacement using this equation. So this is equation 1, this is equation 2. So if you know these two equations, you can calculate the deformations in the case where you have shear forces and bending moments. So these equations are not that complicated. What this is saying is, once you have the internal bending moment, you can integrate the bending moment along the x and divide it by EI, you will get the bending angle. And once you have the bending angle, you can integrate the bending angle, and then you will get the displacements. And since we are using equations to solve, so this method is called equation method. So there are like many different methods to solve displacements and bending angles. So in order to calculate the deformation, you can use a couple of different methods. So, but if you're using these two equations, or if you're formulating the equations to solve the displacements and bending angle, then this method is called equation method. There are other methods as well. So in the chapter, basically they have talked about three methods. I'm going to write these three methods. So one is equation method, which we will talk about today. You also have graphical method, and you also have superimposition. So today we'll talk about equation method, and you have two other methods to solve this problem. So let's take another example. Let's take an example of simply supported beam. And I'm going to draw a cantilever beam also here. So if there is a load P here, and if there is a load P here, you can try to imagine the elastic curves for both the cases. I'm going to draw elastic curve here. So this is how the bending or the deformations looks like for the cantilever case, and this is how the elastic curve looks like for the simply supported case. So at the constraints, you cannot move, right? So because of the load, this is how the elastic curve looks like. Here also, you have constraints, so you cannot basically move at the constraints, but the rest of the simply supported beam will bend something like this. So we know that at this point, displacement is 0. At this point also, displacement is 0. At this point also, displacement is 0. And so there are certain locations we already know the answers of this deformation. We already know what the deformation would look like. So these points, these are called boundary conditions. I'm going to write it here. So this is a boundary condition, this is a boundary condition, this is also a boundary condition. So boundary condition is the points where we already know what is bending angle and what is displacement. So here at this point, for example, we already know the bending angle is also 0 because it's a fixed support. So wherever you have a fixed support, you will see no displacements and you will see no bending angle at the fixed support. And the pin support, you will see no displacements because the pin support cannot move, but you will see some bending angle. So there will be, you can see, you can observe also there is some bending angle here. So the bending angle is not 0. But at this point where the load is being applied, the slope, this is a slope, right? Bending angle is a slope. So you have some slope, but it keeps on decreasing, 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 and then it keeps on increasing. So at this particular point, right at the bending angle is 0. But most important is the supports. So you can just kind of remember that at fixed support, bending angle is also 0, displacement is also 0. At the pin support and roller support, displacement is 0 because no displacements, right? But there is some bending angle. And the equation, I'm going to write the equations because these are super important. So for bending angle, you have to divide by 1 over EI, and then integration of moment, you're going to get the bending angle. And for the displacement, you have to integrate the bending angle. So this is basically bending angle, and this is basically displacement. This is moment, this is moment of inertia, and this is modulus of elasticity. And this is bending angle. And if I want to draw the bending angle and displacements on the figures, this is displacement, and if you draw a straight line and try to make a slope, this is bending angle. In this case, anywhere, this is displacement, this is displacement, and if you want to calculate the bending angle is actually slope. So at any point, the slope is actually bending angle, and the vertical displacement, because of the deformation, because of the shear forces and bending moment, is called displacement. This is equation 1, this is equation 2. So we will use these two equations to calculate deformations. And this method is called equation method, which we will use today. So let's try to do one example. So I'm gonna just draw a simple example and we'll try to solve this. So let's draw So I'm gonna draw a cantilever beam. This is load P. This is length L. So let's solve for this cantilever beam. So what we have to do is we have to calculate the bending angle and the displacement for this case. So let's call this example 1. This is example 1. So this is the simplest case, and we'll try to use equation method to calculate the bending angle and the displacements for this case. So before start, I can just we can just review chapter 7. So this table 7.2 is talks about the boundary condition. So if you have a fixed support, we know at a fixed support the bending angle is 0 and the displacement is 0, right? Similar to this case. This is a fixed support, so you have two things 0. So this table is basically showing the boundary conditions. So if you have a simply supported beam, you have displacement 0. So this table shows you the boundary condition, and table 1 shows you the relationship between shear forces, bending moments, bending angle, and deflection. So for example, if you integrate the loads, you're going to get shear force. If you integrate the shear force, you're going to get bending moment. If you integrate bending moment, you're going to get bending angle, and if you integrate the bending angle, you're going to get displacements. This is what we were talking about. So if you integrate bending moment, you're going to get bending angle. If you integrate bending angle, you're going to get the displacements. Similarly, you can differentiate the deflection and you will get bending angle. So basically you have relationships between all these forces. So if you know one thing, you can integrate or differentiate to calculate another thing. So if you know bending moment, you can calculate shear force, you can calculate bending angles, and accordingly. So these two tables refer this. And then this talks about three methods: equation method, and you have graphical method, and you have superimposition method. So you have three methods, and we'll use equation method to solve for today. So that's basically is written in the workbook. So we can try to solve this example, and we'll use the first method, which is equation method. So for equation method, we have to use equations, and we have two equations. If you want to calculate the bending angle, it's going to be 1 over EI m dx. If you want to calculate displacements, it's going to be integration of bending angle. So all we need to do is we need to calculate the moment. Once we have the moment, then we can calculate the bending angle. So let's try to solve for this. So if we do the summation of forces, if we use equilibrium equations, we can calculate the reactions. So calculating reactions, you do summation of forces, y is equal to 0, x is equal to 0, summation of moment is equal to 0, you're going to get the reactions. So this is the reactions which you're going to get. This is. So the value of this is the reaction P, and the moment is PL. this moment is actually internal bending moment. So we need internal moment, and once we have internal moments, we're going to put in this equation and we'll calculate the bending angle. So we need internal moment. So how we can calculate internal moment? We need to make a cut to expose internal moments, and we're going to use those internal moments in this equation. So if I make a cut, this is what I will get. This is the load. This is the distance x. We are using equation method, so we're gonna formulate equations. And so we'll call this x, and we can expose internal shear force and internal bending moment. So you can use equilibrium equations, which is summation of f of y is equal to 0 and summation of moment is equal to 0. And you can calculate the value of v and m. So v would be equal to negative p, and m would be equal to negative px. So you can use equilibrium equation, you can calculate v and m, right? So this is what you're gonna get. So now you have m, you can use equation 1 to calculate the bending angle. So let's use equation 1. We know bending angle is 1 over EI, and integration of moment dx. So we have already calculated the moment, which is negative px dx. This p is constant, so I can like take this p out. It's minus p over ei x dx. So you can do the integration. It's gonna be minus p. So if you do the integration, you're gonna get x squared by 2 ei. So, and since you have done integration, you also have to put a constant. So the equation for bending angle is negative px squared over 2ei plus c1. So that's an equation for the bending angle. So everyone is clear how we did the integration for x. So if you do integration of x, it's going to be x squared by 2. So that's how you got the negative px squared by 2ei. Similarly, we can also calculate displacements. So to calculate the displacement, we have to just integrate bending angle. And bending angle we have already calculated, which is negative px squared over 2ei plus c1. Which is equal to negative p over 2ei is constant, so I'm going to take it out, x squared dx, plus c1 is constant, so I'm going to take it out, it's going to be 1 dx, or let's just say x raised to the power 0, or let's just keep it 1. So you can do the integration. It's going to be minus p over 2ei is going to be x cubed by 3 plus c1x plus c2. So you also have equation for displacement, which is negative px cube over 6ei plus c1x plus c2. So you can solve this to get the bending angle and displacement, but before you have to calculate C1 and C2. So once you can calculate C1 and C2, then you will have final equations. This is clear with everyone how we have calculated, how we have done the integration. Okay. So now we have to calculate these constants, C1 and C2. So once we have the constants, we will have the final equation. So I'm going to write these equations here. So theta I got minus px square over 2ei minus px square over 2ei plus c1, and displacement I got is minus px cube over 6ei plus c1x plus c2. So all we need to do is we need to calculate c1 and c2, and then we'll get the final equations. So we can calculate the c1 and c2 by using boundary conditions. So we know this was our problem. This is the load. This is the distance L. So if you imagine the elastic curve would be, would be the elastic curve. This is displacements. This is bending angle. These are the two things which we are trying to calculate. And we also know these values at the boundary condition. So at the fixed support, we know displacement is 0 and bending angle is also 0. So we know we'll use boundary condition. Boundary condition is at x is equal to L, because we have decided x from here. So when x is equal to L, our displacement would also be 0 and our bending angle would also be 0. So if you put L instead of x in equation 3 and in equation 4, you're going to get 0 values. So you can use this boundary condition to solve for C1 and C2. So this is 0 when x is L. This is also 0 when x is L. C1 L plus C2. So from here we can calculate C1, which is PL square over 2EI PL cube over 6EI plus this C will go here. So it's PL square over 2EI into L plus C2. So if you solve this, you're gonna get C2 negative PL cube over 3. So now we have solved for C1 and C2. So now we have the final equation. So I'm gonna put final equation theta is, so my theta was minus px square over 2ei minus px square over 2ei plus c1, which is pl square over 2ei. So if I want to rearrange this, I can write theta as, I can take p is same for both, ei is same for both, so 2 is same for both, so it's like p over 2ei into L square minus x square. So this is our final equation to calculate the bending angle. Yes. Yeah, thank you. They're gonna be EI. Similarly, we can calculate for displacement. So the value of displacement is minus px cube over 6ei minus px cube over 6ei, px cube over 6ei plus c1x. So c1 is pl square over 2ei x plus c2. c2 is negative pl cube over 3ei. So if you rearrange this, you're gonna get displacement as p over 6ei minus x cube plus 3l square x minus 2l cube. So this is the final equation for the displacements. So now we have calculated the equations, determined the equations for bending angle displacement for that particular shape for the cantilever beam with one load at the end. So we can use these equations to solve the bending angle and the displacements. So I'm going to write two equations here which we got. So we got p over 2ei L square minus x square. This is our bending angle, and displacement we got is p over 6ei minus x cube plus 3l square x minus 2l cube. This is for the displacements. So if we have some values for the cantilever beam, then we can solve. All right, so this was our x, right? This was our cut. So I'm going to give you some values and I want you to calculate the bending angle and displacements. So if we have, for example, if length is 15 feet and if the load is 6 kips and modulus of elasticity is 29,000 KSI, and moment of inertia is 204 inch 4. What would be the bending angle and what would be the displacement in this case? So I've given you these values. Length, if length is 15 feet, load is 6 kb, modulus of elasticity is 29,000 KSI, and moment of inertia is 204 inch 4. You can calculate the bending angle and the displacements, and you can let me know what are the answers. This entire uh, calculating the equations and entire thing what we did, this is called equation method. So in equation method, basically you have to do the integration, you have to come up with the equations, you have to solve for the C1 and C2, and once you have the final equations, you can solve for the bending angle and the displacements. So if someone has the answer, they can let me know. So you have to feed these values in these equations, and then you have to let me know what is the bending angle. So what I want you to give me is so I'm gonna draw elastic curve for this case. So this is the elastic curve. And you can calculate displacement here and bending angle here. So I want this value and I want this angle. So you can calculate bending angle and displacement at this point. So we know our x was starting from this point, right? When we made a cut, we were deciding values of x from this point. So if you want to calculate the maximum displacements and the maximum bending angle, your x would be 0 in this case. So if you put x is equal to 0 in the equation, you're going to get maximum values of displacement and the bending angle. If you put x is equal to 15, then you will calculate values here. So the answer, so theta is 0.0164 radians and displacement is negative 1.97 inch. Right? So this is